Okay, so this is a walk on a graph. Okay, so here is an interesting aside. So given that we have an introduction to graph theory, let's look at an aside. This is a Kevin Bacon game, very funny. So it was invented by college students in 1994, and their idea was you connect any actor to Kevin Bacon via actors who have co-starred in the same movie. And there is this website called oracleofbacon.org where you can just load up your favorite actor and see how they are connected to Kevin Bacon. Not that you would particularly be interested in Kevin Bacon or this, but it's a very interesting application of networks. And what they did was, I'll give you an example. So let's look at Amitabh Bachchan. Kevin Bacon, how is he connected to Amitabh Bachchan? So it turns out that Kevin Bacon co-starred in a movie called Beyond All Boundaries with Brad Pitt, and Brad Pitt co-starred in a movie with Danny Denzongpa called 7 Years of Tibet, and Danny Denzongpa and Amitabh Bachchan acted in this movie called Dil Jo Bhi Kahe. So this is, so you see that Amitabh Bachchan has a Bacon number of 3. So he's 3 steps away from Kevin Bacon. So basically you can connect Amitabh and Kevin with 3 different movies. It was quite arbitrary how they picked Kevin Bacon and so on. You could, in fact, in India, if we were to do this exercise, we would pick a comedian or someone, and you can easily connect any 2 actors using comedians who would have acted in, co-starred in a lot of movies with lots of people. But this is quite an interesting, and if you are interested in Rajinikanth, you can work out a similar sort of path between Kevin Bacon and Rajinikanth. And in mathematics, there's an equivalent, and this is probably more famous. This is called the Erdős number. Erdős is a mathematician whose work we will study very shortly when we look at network models. But this looked at the number of links required to connect scholars to Erdős via co-authorship of papers. And Erdős was a very prolific mathematician who wrote 1500 papers plus papers with 507 co-authors. And there is a website that gives you details of his co-authored papers and so on, and you can compute the your Erdős number. So the average length among mathematicians is about 4.65 and the maximum is 13. So we will look at these numbers a little later, how this means that it is the diameter of the network is 13 and so on, but I will talk about those in a future class. An example, Paul Erdős wrote this paper with Pavel Hell, who wrote this paper with Zsolt Deng, who had a paper with Christos Papadimitriou, who is a famous author for those of you who have done theory of computer science and so on, who actually happened to mentor somebody we know very well on his master's thesis. So Bill Gates actually has written an interesting paper with Papadimitriou. So which means that Gates has an Erdős number of at most 4, and if he wrote a paper with one of the others on the spread of the COVID pandemic or something in the coming days, then you would see that Gates' Erdős number can actually go down to 3. Right? So now he is 4 steps. So Erdős has a number of 0, 1, 2, 3, and Gates has an Erdős number of 4. And this is exactly what you see in LinkedIn as well. So LinkedIn tells you that somebody is 1 hop away from you, or 2 hops away from you, or somebody is outside your network, which means that in this context it would be that I have a finite Erdős number, but there would be other scientists who have not worked closely with other mathematicians, so they may not be in the network of Erdős at all. Let's say they would not have collaborated with anyone who has collaborated with a collaborator of a collaborator of a collaborator of Erdős. Right? So this is basically how this gives you a glimpse into how these networks are studied and what kind of inferences you can make from these networks. So coming back, why graphs? Why do we need to study graph theory? And there are so many applications. I am just going to scratch the surface for you. Do I know someone who knows someone who knows a particular person? Right? You may want to get in touch with a particular person or so on. This involves identifying the existence of a path. How long is the chain to that particular person? This is a shortest path problem. Is everyone in the world connected to everyone else? You must have heard of 6 degrees of separation perhaps. There are these kinds of interesting concepts that have been thrown around. And this involves the identification of connected components. Who has the most number of friends? This involves looking at connected nodes and centrality analyses and so on, which we will study in quite some detail later on in this course. and are X and Y friends? Like this involves link prediction. Okay. So these are questions that typically interest social scientists. Of course, we are looking at computational biology in this course. We are looking at big data in biology. So what are the kind of questions that we would like to answer here? And if you look at the slide closely, I am just going to change, and you see that the questions are going to change, but the algorithms remain the same. Right? So, is there a way to produce a metabolite X from metabolite A? This involves the existence of a path. Can I produce a drug molecule starting from, can I produce a vitamin molecule starting from a simple compound, right, like glucose or something like that? Or how long is that pathway? So, this has implications for feasibility, economics, and so on. Are all proteins connected to each other by a path? What is the most influential protein in a network? So, maybe you want to look at a pathogen's protein interaction network and target the most connected protein there, and maybe it leads to the disintegration of the pathogen's network and consequently its survival, and will have a positive impact on the disease. Do proteins X and Y interact? Right? Just like this Facebook pop-up that shows up and asks you if this person is your friend. So, can you use, in fact, similar algorithms are used to predict if two proteins are going to interact. And there are a number of problems that naturally map on to graphs. So, this is what makes graph theory very, very interesting, and there are lots of exciting algorithms and exciting problems in computer science and engineering which can be solved using some of these algorithms. For instance, there is a shortest path problem that all of us use very frequently whenever we use Google Maps, but this is also quite important in many other fields. Then you have this traveling salesperson problem. This is exactly what your Flipkart delivery person does every day to determine what is their path, how should they make the deliveries so that they minimize fuel or minimize time and so on. They may have to make a few deliveries in one pin code and few deliveries in another pin code. How do they optimize their travel paths? How do you find strongly connected or connected components? Basically groups of nodes which have a path between each other. We will talk about some of these in detail later on. Graph isomorphism, I will show you later on that it has applications in predicting reactions and so on. I will also talk about what is known as a vertex cover problem or minimum spanning tree problems and so on. The Hamiltonian and Eulerian path problems are basically used in genome sequencing. The K shortest path problem involves looking at paths that are slightly longer than the most optimal path. So, they also have some interesting applications, and centrality measure is something that we will spend quite a bit of time in this course on to understand what are the measures that tell you that a particular node is quite important. So, these are the kind of things that we will look at in the rest of the course. So, that brings me to the end of a quick module giving you an introduction to graph theory. In the subsequent module, I will start focusing a little bit more on graph theory in biology and what are its applications, and lay the foundations for graph models, centrality and so on. See you.